GM Kev,
Oh, hey, how you doing?
not too shabby.
Cool.
Speeding through things today.
That's good to hear.
Yeah, I love those productive weeks. This has definitely been one of those.
Nice. Hello. Yeah, I think we can wait for one more minute. Thanks. Cool. So I think we're recording, so we'll start now. Uh, Welcome to the L1-zkEVM breakout call number 2. This call will have a lot less content than number 1, and in particular, we'll go over the Tamago update by Andrea. He'll be presenting some recent breakthroughs on his Tamago exploration. We'll then go over the project updates from the 7 projects that we have, and then Q&A. So to start it off, Andrea, can you share your screen?
Yeah, hello everyone. One second. I think you need to unshare yours, otherwise it doesn't allow me to. Yeah. Can you see it?
Yeah.
Okay. Yeah. So thanks for having me. So yeah, I've been asked to just give an update on, and actually an introduction to anybody that doesn't know what it is about the project that I'm leading called Tamago. So happy to be able to share that with you. So basically, Tamago is a modification of the regular Go compiler with the aim to be accepted upstream. So there's a proposal in progress for that, which takes the regular Go runtime and all of its ecosystem available for bare metal execution. So execution without supervision from an operating system. So basically, the idea is that we try to take Go at a much lower level, so that we can be, as effective as C or Rust in controlling hardware. So if we look at a regular Go application, which, of course, you might be familiar with, you have the Go runtime running in user space of an operating system, making system calls to the operating system, as you would expect. With Tamago, basically, we don't do system calls anymore to an outside environment, but we piggyback to regular Go code, which actually implements all of the drivers. And in fact, we don't even need a bootloader anymore because we're capable of initializing whatever hardware we have independently in full Go. So we completely remove the need for the bootloader, the operating system, the kernel space, and even the user space supporting execution of Go binaries. The project has been around for some time, so it reached a fair level of maturity. So we have support for 4 different architectures. So we have x86-64, ARM64, and RISC-V 64. And we support a small but solid range of devices, going from physical devices such as USB Armory, which you will also offer in various NXP development boards, to execution under virtual machines on x86, so Cloud Hypervisor, Firecracker, QEMU Micro VM. We can run bare metal Go binaries on things like Google Compute Engine, and we can also run in UEFI. So, for instance, my own laptop is booted by a pure Go bootloader, which replaced my regular bootloader. So this is basically we can bring regular Go in different places. We achieved this by defining an abstraction for implementing arbitrary operating system or not support. So basically, we also re-implemented Linux with this interface. So we define a Rosetta Stone sort of API, which allows with few functions, 6 functions specifically, to enable execution of the runtime in a freestanding environment. The advantage of this, of course, is a dramatic lines of code reduction and attack surface reduction for executing whether on real hardware or confidential VMs. Developing, building, and running Go applications under Tamago is identical to regular Go applications. So the whole Go ecosystem, Go modules, build reproducibility, all the tools, Go vet, Go fix, everything remains the same. There are just different, some compilation flags that needs to be passed depending for the architecture, but they don't affect the code itself. The same goes for debugging. Go trace works as expected, pprof, GDB, everything works as expected. And so, yeah, this means that one can run on bare metal, whether on confidential VM or physical hardware, and import any Go library that you want. And as long as it's not a Go library which specifically targets operating system. So of course, if you're trying to import a library that wants to enumerate Linux processes, of course, that's not going to work because we don't have an operating system. But everything else, cryptographic libraries, formatting libraries, even Tailscale. So this is an example of the Tailscale client running on one of hardware devices that we support. So we can have a Tailscale WireGuard VPN running in bare metal without any operating system support. Very recently, we made a further experimental branch in Tamago, where we are running on even smaller targets. So now we're capable, we have an experimental branch which allows us to run in as low as 5-6 megabytes of RAM, and also to target RISC-V architectures that do not support the D extension or the A extension. So, which means that we can target even smaller target by enabling soft floating point execution. So this is one of the recent projects that we published, which is called COTAM. So you can find under the USB Armory repository, because that's the first hardware device that we published. We have the Tamago repository and all the different applications that we built around this ecosystem. We have, again, bootloader. We have witnesses for transparency ecosystem. We have a trust on execution environment hypervisor. So there's a variety of examples that show the way Tamago works. So yeah, basically this is it, and I would love to take any questions on this if there are any.
Thank you, Andrea. Are there any questions? I have one. There is one, but I'll do one very quickly. Is there a timeline, or do you expect this to be upstreamed into the Golang compiler?
So the proposal that is up there's been a hint by the Go core team that this is going to be considered for 1.27, which is the next major release. So yeah, my hope would be that that in Go 1.27 we have this functionality baked in. I'm actively following any concern or feedback on that proposal. So, I'm pretty speedy on responding to that. So yeah, that would be my hope. Of course, there's no guarantee, but there was a hint that they were considering it for 127.
Okay, thank you. Some said, are there OS level tweaks built in hardware target level?
I'm not sure what that means. So, but basically, the way we frame this, the Go compiler modifications, they do not touch hardware drivers or hardware initialization. So everything is laid out. So specific hardware drivers and also initialization can be implemented outside by different libraries, which means that the Go compiler patch is agnostic in relation to the specific hardware. And so, this way the Go core team doesn't need to worry about erratas and so forth. As far as major trade-offs compared to regular Go, I would say that there are none, in the sense that the runtime, the scheduling, everything works in an identical way. We also have SMP support on multi-core. So the only restriction is that if you try to import a library which is specifically using system calls, so a library that is specifically designed for operating system interaction, it won't compile. So, for instance, if you're importing a terminal application, a terminal library that's designed to send I/O control to the Linux kernel, of course, it won't work. But by definition, that's not a portable library. But everything else can be imported just as regular, and it runs at equivalent speed, if not faster, than under Linux, because you don't have the overhead of Linux managing other processes for you. So personally, I don't see any particular trade-offs compared to regular Go. We're using the same compiler, the same runtime, so it's not like TinyGo, where it's actually a different implementation. It's just the same Go code running, just without system call support.
Cool. Lumi says, have you talked with Geoff for zkVM proving? Last year, I can answer this. Last year, we reached out to Andrea about using Tamago for zk proving, and we have an experimental repository where we showed that it works with Zisk. We did have to, Zisk did have to add in the floating point extensions and atomics, which is why I'm pretty excited for this new experimental branch that removes both A and D. I can share the link to what we were working on here. Guillaume?
Yeah. Right. So no, you haven't talked to Geoff. That was the answer to Lumi. Yeah. I had a question. Actually, two questions. The first one, you said it's considered for 127, right? It's not scheduled.
Yeah, it's being considered, not scheduled. Yes.
Okay, thank you. The other question I had, so you have this branch with removing, what do you say, A and D?
Yes, we remove atomics and double floating point. Yes.
Yeah. So, are there other? There are lots of extensions that Go silently uses. What about those? Are they still? First of all, can you remove them, or are you even looking into removing them? Is that going to become optional? Yeah. What control do we have on the output binary?
So it all depends on the instruction set which is being created by Go. So I think in the end you can control pretty much everything because there's a nice separation between the intermediate representation of the operations in Go and the actual assembly that comes out. So you have different points where you can hijack that. Then Go also has its own Go assembly for, the math library has its own Go assembly. So every time there's a specific instruction that uses a specific extension, it can be, chasened down and it can be changed. Of course, it could be fiddly, right? I only looked at A and D, and that was reasonable. The patch is pretty reasonable. But for instance, if you ask me about C flag compression, I would assume that's a little bit more complicated. So I would say it highly depends on the specific flag that we're talking about.
Okay, thanks. And by the way, what about F as an option, as an extension?
So I just pointed out the chat the flags that we support now. F, I think it can be done. I think it's possible. You might lose some types. I think it could be. I think it could be possible. Go has an internal abstraction for deciding which registers to use in order to do internal calls and storing data. And I think that abstraction supports not having floating point at all, because I think it does that at least for one ARM implementation that I know of. So in principle, I think it's more fiddly than the patch that I did now, which I think is fairly compact, but it is possible. It's theoretically possible. Theoretically, you can do it.
Okay, thank you.
Yeah, I think most of the floating point, the fiddly parts are to do with the assembly, like floating point move. So when we looked at it, it did seem very tractable. It's just, a bit fiddly.
I think the major issue is that there are a lot of intrinsics. So there are some basic rules for generating assembly, but then there are some intrinsics where Go just takes over and provide optimization like min, max, and other things. So that's where it can become tricky. But I had friends that implemented entirely different architectures using this abstraction from scratch, and which means that potentially you can support any complete instruction set as long as it's Turing complete. You can do it. So I have no doubts it's not a theoretical problem. It's just a matter of putting the effort into it.
Cool. All right. Thank you very much for this. And thanks for presenting.
My pleasure. Thank you for the opportunity.
Thank you. To move on to the project updates, Ignacio, are you here?
Yeah, I will share the screen. Give me a second. Can you see my screen?
Yep.
Cool. Let's do this. Yeah, so we got some updates regarding project number 1, which is related to the execution witness for zkEVM. As a quick refresher, what is the execution witness? Is basically the information we have to pass to the guest program in order to allow it to execute statelessly. So regarding updates here, developer Uche has been exploring benchmarking this ng new payload with witness RPC. that is already implemented in some ELs, but the main idea here for the exploration is trying to understand how much using this RPC can help into improving the prover performance pipeline. Because if we don't use this RPC, what the way we have to resolve proving blocks is basically doing a separate call to the bug execution witness, and this basically means having to re-execute the block twice. So basically, the main results here is that how much this RPC helps into the proving pipeline seems to differ a bit depending on which EL is being used, but this is mostly the root cause of this is mainly each EL haven't really been optimizing this a lot. Some of them use some tricks that might not be used in others. So yeah, there's some difference there in how much utility we can get from it. But the big insight is that the main bottleneck seems to be the transport layer used in the RPC. So the way the engine API works today is that you use JSON RPC, and for the worst cases in the execution witness, we have pretty big structs that we have to serialize and send as an output. So he has been exploring using maybe other transports for this, where we can get up to 20x performance improvements in worst cases. So if you are more interested in understanding more about his work, there are two reports that he wrote. I will share the slides later. So yeah, you can look more into it. So this effort is part of a bigger discussion happening today about using SSE in the engine API to optimize this overhead of using JSON for serializing the output. Some days ago, Julio from the Aragon team has created this ETH research post with some other benchmarks. And also Barnabas from the PandaOps team in DF has proposed this more formally in the specs. So I will really encourage people to look into these two links. And as a last update for this project, we are very happy to announce that we have been working and released the first execution witness generation specs. You can find this in the execution specs repo in the project/zkEVM branch. And this release basically has the first complete specs for this canonical witness generation logic, plus around 12,000 field tests, which now has this new execution witness field that contains the execution witness for each existing test field with Amsterdam. So before making the formal release, and to gain more confidence that it was doing what we wanted, we compare it with Red, which also has execution witness generation. I already knew that Red has multiple inefficiencies, so it was a good experiment to compare both. And yeah, basically we found multiple changes to be done in Red, which resulted in some PRs, so they can evaluate them and fix Red to be to generate canonical execution witness. And also this allowed us to find bugs in the specs too. So this basically means that we have more confidence on inviting our ELs to start comparing with these specs. So the concrete ask for action here for other ELs is basically to run all these fixtures in the release in stateful mode as usual. You make the EL generate the execution witness for the test block, and you compare it against the execution witness field from the fixture to see if your EL is generating the execution witness in the same way that the specs. Of course, since this is the first release, there might be cases where there might be bugs in the specs. So if you have any questions or do you think that is the case, please contact some of us in the Discord server. So the next steps regarding this are basically start creating more tests for the execution witness border cases, so we can keep hardening the implementation. And yeah, that's mostly it. I don't know if there's any question. Yeah, Guillaume?
Yeah, what did you focus on REST knowing? I mean, okay, let me rephrase the question. Did you test with Geth at all? Because Geth and REST are incompatible, and I would argue REST is buggy. So why pick the one client that is no longer concerned with Ethereum?
Right. So the specs were written for first principles. So the specs aren't really based on any EL at all. The reason why I choose Red is because I already knew it has many bugs from my perspective regarding what I think is the correct way of generating the execution witness. So I already knew that Red and the specs that I wrote should disagree on multiple cases. So that's mainly the main reason why I chose Red, not really because of anything else. I created actually these PRs to fix these inefficiencies, and they aren't really merged yet. So, but in any case, what I wanted to do is harden the specs and be sure that in this first release, I wouldn't be giving a lot of ELs something that might have a lot of bugs. So it was mainly for hardening the specs. But I'm more than happy to help Geth or any other EL client to run these fixtures and see if we find anything else.
And how do you run the fixtures?
Right, so the fixtures are exactly the same as you run today in ELs, but the fixture have an extra field called execution witness, which has basically the execution witness that the specs consider to be canonical. So the way you have to do this is you run the test as usual, but you also generate the execution witness in your EL that you think is correct for this block, and you compare it against this new field in the fixture. So it's basically kind of the same of you run the test and you calculate the new state root and you compare it to the fixture state root. Well, this is kind of the same. You run the test, you generate the execution witness that your EL thinks is correct, and you compare it against the fixture execution witness.
Okay,
Does
but
that make sense to you?
well, kind of. Do you have like something like block test? Like, does the client need to write some kind of specific binary to be able to execute all that stuff? And is it documented anywhere?
No, you don't have to run anything new apart from supporting generating execution witnesses. There's no new binary needed or anything like that. It's
Okay,
like a
so
new field appears in the current fixtures format.
okay. Thank you.
Maybe a question for Francesco when he gets to his update. It would be good to sort of elaborate on the difference between debug execution witness and engine new payload with witness, because I imagine most of the zkVM teams are calling debug execution witness at the moment, and yeah, just specifying how it would change. Ignacio, on this, I guess, would it be useful for the ELs to also experiment with the stateless input bytes and stateless output bytes?
Right. I was going to mention this in the project 2 update,
Okay.
but yeah. And just as a last comment for Guillaume, in the release description, we explain a bit more in detail how to use this. So if you are going to give it a try, just read that. And if it's not really clear, just let me know and we can keep improving.
Makes sense. Yeah, I guess to clarify, none of this should be new to the EL teams if you're already testing using East. This is just adding in execution witness to your blockchain fixtures, however you ingest them currently.
Okay, so if there's not any other question, I can keep with giving project 2 updates. So project number 2, as a refresher, is having a set of specs for what the guest program should do. So I don't have many slides here because a lot of work has been happening in the execution specs repo, but we have in the same release that I just mentioned for the execution witness, in the same commit, you will see a kind of first draft implementation of the guest program. Here I have like a screenshot of this like entry point for the guest program where it gets the input bytes and basically executes all the logic and returns the output bytes for the public inputs. So I would say that if you are an EL working in guest programs, it might be interesting to start looking at these current draft specs. We still want to polish it a bit further, so you might expect some changes happening in the branch. And we also want to start creating more tests for the guest program because we need to cover a lot of cases of invalid inputs, missing information, and things like that. So probably we'll make like an official first release, a first official version in the next release. But you can start looking at it, and yeah, if you have any feedback, we are more than interested in hearing that. And related to what Kev was saying before, in this same release, we already added 2 extra fields in the fixtures, which are called stateless input and stateless output. So you can start doing some kind of early experimentation of at least trying to deserialize the inputs and testing how this works, because we in the current specs we are using SSC for serialization of the inputs. We found this is like a neutral choice of encoding for guest programs, but we also know that currently ELs don't have like a formal need for having SSC library. So as a first step, at least just trying out SSC deserialization with whatever library that you might be planning to use in DL might be like a good first step. So yeah, that's everything for project number 2. I don't know if there's any question. Yeah, Guillaume?
Yep, sorry, it's me again. Why do you pass in the stateless input? Why do you pass the entire chain config?
You mean like a concrete question about the stateless input structure?
Yeah. It's a spec question, yes.
Yeah, so this chain config is basically enough information for the guest program on how to configure the EVM. You can argue that we can avoid this and simply assume that is like current mainnet configuration or something like that. But for testing, this is a bit complicated because the testing framework defines really custom forks. So we think that the most flexible style is to simply provide the chain configuration as the inputs. So the same guest program can actually execute multiple chain configurations, because it might be required for running tests with really weird setups, apart from like the main use case, which is running mainnet blocks. But yeah, I mean, this is something that we have been discussing a bit, and we are still open to like thinking if there are better options or similar. But that's kind of the main thinking. Somnat?
So just a clarification for the test. So currently the ESTs sort of have this assumption that the blocks are going to start with the genesis. That is not sufficient to test the witness and how it is being handled. For instance, the MPT for the stateless processing is going to be different, and I think ESTs do not test it at the moment. So you need specific tests to verify that your MPT is working correctly for the stateless case, because it's a sparse MPT. It's like different.
Right. Yes. So this is related to all these new tests that we are planning to include in the next weeks, because there are a lot of new cases that are important for the guest program verification step. Yes, regarding the MPT, because you have like a partial view of the MPT and you have to check that the provided information is correct, and also for the other fields. So yeah, I mean, there are a lot of new test cases that should be added to cover all this. Guillaume?
Yeah, just a question, because from what I understand, to run those tests, you're going to need some pretty beefy backend, right? Like those guest program are going to need some setup with like graphics cards and things. Otherwise, it's going to take forever. How do we? Yep.
And not because and when you run this test, you are just lead it start info. You don't have to create any proof of these blocks. It is just like trying to see if the stateless execution of the block is working correctly. It's not about generating proofs or similar. Yeah.
Okay.
Ignacio, there are some questions, RLP and SSZ. My thinking is that we can only choose between RLP and SSZ. I know some zkVMs use like bin code or archive, and I think we just want to go whatever is more performant here. I don't know if you had any thoughts on that.
Yeah, I think that the encoding part is something that we have to explore more. From some benchmarks that we did a while ago, it seems like RLP was pretty slow compared to SSC improving, but I know this is something that we can change and keep exploring. This is not like something set in stone at this point.
Okay, sounds good. Marcin, do you want to share your slides?
Hi everyone. So today we're doing a quick recap of Project 3, zkVM Guest API standardization. All the standards discussed here live at zkVM standards repository. We accepted 3 standards so far. First is the RISC-V target triple. This defines the minimal 64-bit ISA for proving Ethereum blocks. RV64IM is for efficient arithmetic, plus the extension to handle misaligned memory accesses transparently, which prevents compiler edge cases from making blocks unprovable. Second is the I/O interface. It consists of 2 functions, read input and write output. This gives guest programs a portable and zkVM independent way to receive private inputs and emit private outputs with 0 copy support for VMs that preload inputs into memory. Third is cryptographic acceleration C interface. It's a C header that exposes EVM precompiled equivalent operations through a common C API. In this way, guest code doesn't need to know anything about the underlying vendor implementation. A quick reminder on what these standards mean in practice for zkVM vendors. If you're currently running 32-bit zkVM, migration to 64-bit RISC-V is expected. The target we standardize is a 64-bit machine, and that's not optional for EF use cases. On the Rust side, the Rust target is bare metal. without operating system and without standard library support. That's why zkEVM SDKs must be no STD, must be no STD compatible. If any code in the runtime of a zkEVM depends on STD, it simply won't compile against this target. Yeah, also zkEVMs should provide I/O and accelerator implementations as part of the SDK. Now for the standards we still need to close. Execution termination semantics has been already reviewed by many stakeholders and is ready to accept. In short, it standardizes what happens when a guest program terminates, either cleanly or abnormally. Successful termination may generate a valid proof, but proofs of failed executions must fail verification. This is a security requirement and also a matter of developer experience. We'd like to move to accept this standard as soon as possible. If there are no blockers, please signal your support. Finally, memory layout restrictions. This one needs more attention. Very few vendors have reviewed it so far. And the core idea of the proposal is that each zkEVM vendor is free to define its own memory layout through vendor-specific linker scripts. So if you haven't read yet the specification, please do and leave the feedback. We also would like to accept and merge that standard as soon as possible. And that's basically all from my side. Are there any questions?
Lewis said, how much effort would it be for zkVMs to support F and D RISC-V instructions? A big effort. Just curious. I think the way that this supports it right now is just dispatch into some precompiled library. My opinion is that to support FND, there should be some like motivation to support it, and not like just because like it extends the capabilities of what the zkVMs can do. Like the STF doesn't require FND.
Yeah, it's good point. I'm just worried about like some compilers that might need extra work to remove these extensions instructions from the compiling process, and we might also be creating more a bigger burden on the compiler side, Java, the language compiler side. Just because it doesn't use the OS anyway, so why being restrictive instead of being more relaxed if it doesn't introduce entropy in the system?
Right. Yeah. I think that makes sense. I think the main one was actually Go, which was why Andrea's presentation was really good, because he showed that possibly we can just remove the F and D RISC-V instructions with Tamago. But yeah, I definitely get your point. I guess one thing maybe to call out on Marchin's slides is the part about the Rust SDK, meaning that even if your zkVM supports RV64IM, a lot of the SDKs currently, because they're using forked, because the compilers are forked, you can have an SDK that is that uses the std library, but once you move to RV64IM, the SDK also needs to be no STD unless you create another one, because all of the guest programs will be relying on like your SDK. If there are no questions, I think we can move to the next project. Thanks, Marcin.
Thanks.
Francesco.
So I've been working on the Lighthouse implementation. So in regards to feature completeness, we've got the kind of core features implemented. So proof validity, using this concept of the proof engine, which I introduced in the last call. And then in addition to that, we've got the network proof sync protocol implemented as well, using the RPCs which are defined in the spec. And then around that, we've got reasonably good integration and unit testing. So pretty happy with the code coverage of these new features that we've introduced. There's a bit of a challenge in regards to kind of the networking layer around proof capable peer discovery. And this was flagged by Manu. But I've got a proposal of how we can address this using a new RPC method. And I'll talk a bit more about that in the next slide. But I've opened a PR which essentially uses this RPC and kind of optimizes the naive proof sync protocol. We've got a few small features to implement. These shouldn't be too difficult. And then kurtosis support is kind of the final task. But yeah, I feel like we're making pretty good progress, and we should be feature complete in the not too distant future. So a bit more on this execution proof status RPC. The main problem we have is the first problem we have is discoverability. So the kind of the idea is that we will kind of announce to the network using our ENR that we support proofs. But the problem is that ENR is only visible, from what I understand, to the node which is initiating the connection. So the node that receives the inbound connection request will not know that the node connecting to them supports execution proofs. So there's this asymmetry. And in addition to that, we have no awareness of the proof, the kind of the sync status of proof capable peers that we're connected to. So we don't know which peers have validated up to which slot using essentially. So we don't know which peers are good to attempt to sync from. So the kind of the high level idea is to introduce this execution proof status RPC, and this will be invoked eagerly on connection by the peer who is making connection if they see that the target peer is advertising the the execution proof support on their ENR, and that way the receiving peer also knows that the connecting peer supports execution proofs. And this we may be able to do this with kind of deeper modifications to pre-existing code, but to keep this forkless, we don't require any forks or any changes to kind of pre-existing RPCs or data types. I suspect this is going to be the cleanest solution. So yeah, high level idea is that the body of this RPC message is going to be the slot and the block route that the peer sending the message has managed to verify using execution proofs. And then the receiving peer will cache this result, and it can kind of strategically direct requests based on this information. And in terms of one of the benefits, the peer who receives this status update will be able to determine if like a range sync is going to be more efficient than doing a by route sync, where by route is essentially by block or by slot, whereas range is you can sync a range in a range of block proofs in a single request. So that's the core idea. This isn't finalized or added to the specs. I'd like to speak with Manu and other individuals working on this effort to see what the opinions are. And then to proceed, can you see?
Yeah.
Not sure. Can you see the new diagram?
Yep.
Okay, cool. Yeah, I just threw this together at the last minute, so apologies that it's not very pretty, but I just wanted to add some context in regards to what Kev asked. So this at the top is essentially the current flow that we have for proving. So we have some consensus layer validator. They're connected to an execution layer. They invoke the engine new payload method and receive the result from the execution layer. They then subsequently take that payload and include it in a engine request proofs, essentially just a proof request to the prover, who then has to kind of enrich or fetch the execution witness from an execution layer that they maintain. And there's a few complexities here. We kind of assume that the prover's execution layer is in sync with the EL. If not, then I guess with the peer who is requesting the proofs. If not, then I guess they could just kind of engine new payload, the payload which they receive from the validator, but that adds re-execution and it's inefficient ultimately. And a nice kind of way to address these complexities is to include the witness in the response from the EL. So new payload with witness essentially sends back the witness in addition to the result, and then the witness can be included in the request to the prover via in the request to the prover. So in this construct, the prover can be stateless, which is a pretty nice property. There's still some open questions because we don't know if we're communicating worst case 100 over on the order of hundreds of megabytes of witness data over the network between remote peers. It may not be efficient. So there's still a number of open questions, but on a high level, this kind of illustrates the the changes that Ignacio touched on, that developer Uche has been working on. Does that cover enough, Kev, or do you have some context to add?
Oh no, I think this is perfect. We can discuss like the rest of it async, I think.
Yep.
Cool. Thank you. Okay. Thanks, Francesca. Han.
Yep. Can you see my screen now?
Yep.
Okay, so I'll give some update on the Project 5 proof infrastructure. So we have our DIY build tower in preparation. Once it's ready, we can start to use it for benchmark. It's a 4x4 cluster, so 16, 15, 19 total. And big thanks to EF DevOps team and Panda Ops team's work on this. And on the zkEVM integration side, we have added the disk proving cluster integrated, which allow us to test on our 4x4 machine with 16 GPU in the future. And we also upgrade the SP1 to V6 and publish the proof image with CUDA enabled. And on the zk attester side, we have drafted the proof node API for the zk attester to request for execution proof. And basically, there are just three API. One is the request proof with the new payload request in SSD and with the proof type that the attester would like, and asynchronously. And the attester can use the server-side event to subscribe to the proof result. And once the proof is ready, it can use the deterministic endpoint to get a proof that is parameterized by the root and the proof type. And any feedback appreciated on the proof node API that will be used in the chart as the API to communicate with the consensus layer that Francisco just shared. And next, I'll be focusing on the cluster integration that allows us to test our 4x4 cluster and finish the implementation of proof node API on the zk boost and integrate with consensus layer and start to experiment the cluster proving on a 4x4 cluster once it's ready. And here is the server per server spec. And I guess we will have to experiment a bit to get the optimal performance for the provers. And hopefully, eventually we can make a document that is be able to people can use that to reproduce the setup. Yeah, that's my update.
Thanks, Han. Any questions? And while we're going through that, Ignacio, do you want to share your screen?
Yes. There's no any questions for Hans' presentation. I can continue.
Yeah.
Okay, cool. So regarding project number 6, I will go a bit fast because we don't have much time. Project number 6 is basically around benchmarking everything that is relevant that might have consequences for the protocol. So the most obvious one is proving stuff, how fast we can create the proofs, and if that's within the bounds that we have for within the protocol. So this is related to this, for example, the CapEx and OpEx, how much money do we have to spin up these proving clusters, which is the optimal configuration of the cluster for each zkEVM. Then we need all these data sets to really know which are worst cases blocks for computation, for stateful operations. We have all this EL witness generation latency that developer Rucher has been working with. But apart from proving, we also have to gain more understanding of proof verification and which are the consequences of these proof verification latencies on proof propagation within the network. So yeah, this project is basically around benchmarking everything that is relevant. So we already touched on this a bit in 2 series articles, mostly regarding on proving and repricings. But yeah, there's this project number 6 is about basically measuring everything that is relevant. So as updates for this month, we released, so I'm sorry. So there was like a new release in these tests for benchmarks, which is basically adding support for Fusaka in benchmarks, which is mainly relevant for ModX new repricings. So using this new release, we rerun all these benchmark cases in this 8 GPU proving machine that we have. And we publish the results in the dashboard, which here I have the link. I will share the slides later if you want to take a look. This proving machine is not optimized for CISC. This is mainly all this work that Han and PandaOps is working on now by building their own cluster. So, but yeah, I mean, the main goal here is to have like a really polished pipeline to measure worst case blocks for Ethereum and figure out which is like the repricing required to really support block proving for 100% of the blocks. So the next steps around this is I will try to integrate Maria's analysis pipeline that is she's using for G-star repricings. Because at the end of the day, after you do the measurements, the rest of the work that you have to do for repricings is to analyze these measurements and get to the new repricing. So the analysis part can be shared with the same methodology that we are using today for G-star. So I will be exploring this more in detail next, so we can have like an end-to-end pipeline where we do the measurements in the proving cluster, and as the end result, we have the same analysis results that we are using for G-star. Apart from that, we also release a new dashboard, which is the proof verification dashboard. This is formally measuring the proof verification latency for each zkEVM. This is pretty relevant for network propagation of the proofs if we are assuming that proof verification is required before keep propagating the proofs within the network. So the way we are doing this benchmarking is basically running the proof verification in machines that comply with the IP 7870, which are the hardware specs that we expect from validators. The dashboard basically does this for two machines that are really close to what the EIP defines as hardware requirements for testers. So yeah, I invite people to simply open up the dashboard and see the results. Apart from proving verification latencies, apart from proof verification latency, I also show the proof size of each zkEVM and also the current security bits pulled from the SoundCalc project from the cryptography team in DF. So trying to show all the angles here because, of course, the more security bits you have, that might influence in the proof verification latency. So in order to have like a fair comparison here, the three things are shown: proof verification latency, proof size, and security bits. And as a final update here, this is coming from Rafael from PandaOps. He added support for custom RPC calls after benchmark runs in Benchmarker. And for us, this is pretty important because if we want to have a way to capture execution witnesses for particular stateful opcodes, such as balance, store, and store, we need to actually run these benchmarks in stateful environments. And what this feature from Benchmarker allows is to leverage Bloatnet to capture the execution witness in these worst cases of stateful opcodes. So this is great for us because we didn't have like a good way to do this from the East fixtures because East fixtures don't really have like a big state. So yeah, thanks a lot, Rafael, for implementing this feature. And that's all from project number 6. I don't know if there's any question.
While we look for questions, Cody, do you want to share your screen?
No questions?
I think you can go.
Okay, cool. Well, yeah, thanks everyone for making it this far. This is a quick update on security, project number 7. I posted a link to these slides because they have some links in them you might be interested in the Zoom chat. But yeah, I can start this. So yeah, first of all is on RISC-V compliance testing. There are these standard architecture tests here that are used, across hardware, the hardware industry for testing RISC-V, and that's tested using this framework with this name. Maybe I think you pronounce it RISC-V. I'm not sure, but it's kind of a weird, messy framework that was a little hard to integrate, but and I'm happy to say that they've gotten rid of that. So now there's something called Act 4, which is being announced here on the forums, the RISC-V forums, and it's easier to integrate, and it also has some new tests. And they're going to have a better schedule of releasing these things and making it clear what are the canonical versions of the various pieces of this. So yeah, I'm working to integrate that into our test monitor. SoundCalc, I'm speaking here a little on the behalf of the cryptography team. So they had asked teams to integrate into SoundCalc, which is this Python tool that they use to clearly write down the security analysis in terms of number of bits of security of the protocols, the ZK protocols. They have finished these integrations, and you can see a summary of the results at the link here. It's great work from them. Thanks for everyone who contributed there. There's this interesting paper that got a lot of attention maybe a month ago about formal verification, where this author, Nadim Kobesi, I think is how you pronounce it, found some bugs in formally verified libraries, including within the formal verification boundary. And I think this is interesting for us as sort of like level setting about what we can expect from the methods. Not to say that we expect to find bugs, but rather it helps us to know what to look for. There's a very explicitly written down framework for describing the formal verification boundary and some helpful tips about how to audit these things in this. So that'll be useful for us as things move forward. Oh, excuse me, I lost my. Oh, it's not advancing. Here we go. So yeah, on this final point, I've been trying to create starter specs for some of the zkVMs, including Zisk, or I started with Zisk. So I used AI to translate the implementation to Python, and then it's all reinforced by test vectors. And yeah, this has been reviewed by some of the teams, and I'm getting positive responses on the results there. So maybe we have some progress on creating specs for the protocols. And also, I've had a lot of conversations about what the value of the specs are, like who they're for, and where they should go in the consensus layer specs. That was a proposal that I think most people agree is doesn't make sense. So some progress on the value of specs, broadly speaking, how they should be targeted. And that's all for me. Thank you.
Any questions? We did Q&A sort of interleaved, so there's not going to be a massive Q&A part at the end. Any questions for Cody? Okay, cool. I mean, yeah, we can also take questions async as well in the Discord channel. And as time goes by, I believe project 1 and 2 should have very shorter updates. If there's nothing else, yeah, thank you all for coming to the second L1-zkEVM breakout call. I'll see you in a month.